Hello everyone, I am Aniruddha from IIT Indore and today we are meeting for the week 7 discussion on the NPTEL course on measure and integration. This week we have seen how to define the integral of a non-negative simple measurable function and for non-negative measurable functions. So let me just write it down. So we have seen integral of non-negative simple measurable functions and integral of non-negative measurable functions. And of course, the properties of these things, which include linearity of the integral, and if f is integrable, then mod f is integrable, and all those things. In fact, towards the end, we have also seen how to define the integral of any measurable function by using the positive and the non-positive part. So we have seen the integral of any extended real value. Sorry, extended real value measurable function. Okay. So I'll just mention how we define it. Suppose we have a simple function s from x to r star is simple. Then by definition, s at any point x is given as ai phi aix, where ai's are subsets of x, they are mutually disjoint, and their union becomes whole of x. So this is the definition of simple functions for us. And moreover, if it is measurable, then there is the additional assumption that this AI is all come from the sigma algebra S, which makes this X a measurable space. Okay. And then given a measure mu on this sigma algebra S, we define the integral of S with respect to mu. We define it as sum of AI, mu of AI. So it is quite natural to define it this way, because what we are essentially doing is, say this is our set X, and this is the non-negative real line. Of course, it starts from here. This is the 0 point. Okay. And then what we are essentially doing is given sets AI. So perhaps this is A1, and then this is A2, and so on. Somewhere maybe A3. And we never say that these simple functions cannot have repeated AIs, right? So perhaps A4 and A1, they have the same AI. So this is say A1, this is A2, and then this is A3, and so on. So what we are doing is, if we are saying that let us look at the sum of AI into mu AI, we are looking at these rectangles. So I have missed some, something in between, but yeah, that can be considered as 0. So let us look at this area of these rectangles, add them up. That is going to be the area under, well, let me not call it area in the sense that I'm just calling it area under S. And that is quite intuitive, because in Riemann integration, the whole motivation of defining Riemann integral was to get area under curves of continuous functions. So, okay, given this definition of simple function, we extend this to non-negative measurable functions by looking at sequences of simple functions that converge to the given function. And that is possible because of some construction we had seen in the previous week. And later on, just okay, maybe I'll write it. Given f from x to r star, non-negative measurable function, we define integral f with respect to mu as this limit of integral essence with respect to mu, where essence are non-negative simple measurable functions with the property that Sn converges to f. So this convergence is pointwise. That means we take any point x in the capital X set, Sn x converges to f of x. And then finally we defined that given any measurable function, so till now we had this assumption that this f is non-negative everywhere. Given any measurable function, we define integral of f with respect to mu as integral of f plus with respect to mu minus integral of f minus with respect to mu. Again, this is quite natural. Why? Because let us look at I mean, not simple function as in the sense of simple functions we have defined. Simple to draw functions. See, suppose this is our function. Somewhere it goes below. Then what we are essentially doing is to calculate the area under this curve. Let us look at this area. It could be calculated using the previous definition of non-negative functions. So this is our f plus. And then let us look at this area. But this is minus f minus. So we have to subtract it because it is in the negative direction. So this definition is also intuitive, and moreover it helps us prove that this integral is actually linear. Prove that integral f du mu is linear. That means integral of af plus bg d mu can be written as a integral f d mu plus b integral g d mu. Again, some property that we really want it to satisfy. Okay, so this was sort of a summary of week 7 contents. Now, if you have any doubts, you can ask me. So I think somebody had joined in between. Let me ask them who had joined. Prasandeep, do you have any doubts?
Yes, sir. I have a doubt from last week.
Uh-huh. Week 6, you mean?
Lectures. Sir, there is a problem that can that is measurable if and only if its modulus is measurable for all f such that x2 real number r. Then x is equals to then the sigma algebra s is equals to power set of x. That I am not able to prove it.
Uh, so what is your question? Your question is that f is measurable if
If
and
and
only
only
if mod f is measurable.
measurable for
Uh-huh.
all f for all function f such that x2 real number r
For
for
every
every
f, okay,
for every function. It has
uh-huh.
given that every function f such that x2 real number r, not extended real number but restricted to only real number.
Okay, okay. Mm-hmm.
Then it says that then the sigma algebra, our measurable space, it
Mm-hmm.
is equal to power set of x.
Okay. We have to prove this. Is it? Do we have to prove this? Hello.
It's a question of assignment actually.
Oh,
It,
okay, okay.
okay.
Is that assignment already graded or not?
I have tried it. but I have seen this result in the book suggested
I
by professor,
Yeah,
and it is
that is
given
fine.
in the book, but I am not able to prove it.
Okay, that is fine. I am asking you whether that assignment is already graded. Did you get the marks for the assignment?
Yes, sir. Yes, sir. I have.
Okay, because if not, then I cannot discuss it here. So, because if the time is still there to submit the assignment, then I cannot discuss it. Okay, so okay, fine. If that submission deadline is gone, then how to prove this is that, see, what we are saying is for every f from x to r, f is measurable if and only if mod f is measurable, right?
Yes, sir.
And there is this what do we say? This equivalence that f is measurable if and only if f inverse of E belongs to S for every E in the Borel sigma algebra of R. Is it
Yes,
right?
sir. Yes,
Okay.
sir.
Now, let us look at any set in capital X. Let A be any set. So, what I will do is let us define a function f from x to r as follows. F at x is 1 when x is inside A. It is minus 1 when x is not inside A. Okay, is this right? This is the definition of my function. Hello. Yeah, Prashandeep, are you there?
Yes, sir. I'm listening.
So this is the definition of my function. What can you say about mod f? What is mod f equal to?
It is the constant function.
It is 1, right? For every x. So, sorry, every x in capital X. So therefore, is mod f measurable?
Sir, it is a constant function.
Yeah, yeah. But is mod f measurable then?
Yeah, because it is a constant function.
Yes. So therefore, mod f inverse of any set E, there are only two possibilities, either empty or whole of x, right? If one belongs to E, and if this is x, if one does not belong to E, which is in both the cases inside the sigma algebra S. Therefore, mod f is measurable. But then by hypothesis, what do we know? This implies, in fact, this is same as saying that f is measurable, right?
So it said that for every function f such that x to r,
Yeah.
this result is true.
Yeah, but then for this function also this is true, right? Because mod f is measurable, f is measurable. Are you understanding what I'm trying to say here?
Yes, sir. You have defined a function such that mod f is measurable if and only if f is measurable.
No, no. This is the hypothesis, right? I have not defined a function such that this happens. This is my
Yes, sir.
hypothesis.
Yeah, it is given in the.
But then mod f is measurable, which means that f is measurable, right? So,
Yes, sir.
but f is measurable means what? This implies the pre-image of singleton one. This must belong to S. Is singleton one a Borel set?
Yes, sir. Yes.
Yeah. So, but what is pre-image of singleton one? Can you tell me?
It is at A.
It is A, right? This is A. So A belongs to S. So what I said is, you start with any set in X, that set is inside S. What does this mean?
It is f is measurable.
No. See, f is measurable, we already proved, right? Okay, see, I think there is some communication gap. What do we have
Yes,
to
sir.
prove? You tell me. You tell me what do you understand by the statement of the question? Yeah, I'm asking you.
Yes, sir. Mod f is measurable if only if f is measurable. You are asking that?
No, no. I am asking you, what do you understand by the statement of the question? There is a question you want to solve. What do you understand by that? Forget about whatever I have written. There is a question in front of you. The question says that whenever mod f measurable and f measurable are equivalent, we have to prove that s is equal to power set of x. What do we mean by that? What do we have to prove actually there?
Obviously, the sigma algebra should be equal to the power set of x that we
But
have to.
then, what do we have to prove then? How do you prove that these two sets are equal? Sigma algebra is a collection, right? Power set is
Yes.
also a collection. How do you prove that they are equal?
Then the yes, sir. The every set in the every subset of set x is measurable.
That is what we have to prove, right? Because
Yes, sir.
sigma algebra is already contained in the power set. It is
Yes,
enough to
sir.
prove that the power set is contained inside the sigma algebra. Then these two collections would be equal.
Yes, sir.
Okay. So let us start with any set inside X. So I have started with A inside X, that is arbitrary set. What
Yes,
I
sir.
will do is, corresponding to this set, I will define a function for which mod f will be measurable.
Okay.
Okay. So what I will do, let us see, there are many ways to do it. This is the simplest way. So let us define this f as, 1 whenever x is inside A, minus
Yes,
1
sir.
whenever x is not inside A.
Okay.
Okay, we don't know whether f is measurable or not because we don't know whether A is in the sigma algebra. So, Acha, can you
Okay.
tell me whether f is a simple function?
F is
Prasanjit,
yeah. It's a linear combination of chi function. That's the
which
definition.
which two chi functions?
If f1 we can define f1 such that x belongs to it, and then the value is 1, and it not belongs to it, then is equals to 0.
Yeah. So, how do I write it in terms of the characteristic functions? See which two sets are involved, or how many sets are involved first of all.
X and a complement.
A and A complement, right? Now the only two possibilities are either a point is inside A or the point is inside A complement, correct?
Yes.
So the two characteristic functions that are involved are chi A and chi A complement,
Yes, sir. Yes, sir.
correct? Now, what happens when X is inside chi A?
Sir, can you repeat?
What happens when X is inside chi A? I mean, oh, sorry, not inside chi A, inside A.
Inside it, then obviously the value is equals to 1.
So we want one whenever X is inside chi A, right? Inside A, right?
And
Yeah.
yes,
And here, for the second set, what do we want?
if it is belongs to complement of a, then the value is 1. Oh, yes.
No, it is minus 1, right?
Yes, yes, sir.
It is minus 1.
Yeah,
So it is
minus,
plus
coefficient is
minus.
minus.
Yeah. So this is 1 times chi a plus minus 1 times chi x difference. So this is a
Yes.
simple function, right?
Okay.
Now, okay, this was just an observation, nothing to do with what we have to prove. Okay, so given this f, what can you say about mod f? Mod f is a constant function one, right? As you
Yes,
said.
sir.
So
Yes,
can
sir.
you say that mod f is measurable?
Obviously, sir, it is a constant function. So it is a
So the thing is obvious. It is measurable because every pre-image of any set is either empty or X,
pi
and
or
which is
either.
always inside. Right?
Yes, sir.
So mod f is measurable. Now let us
Yes.
look at the hypothesis. The hypothesis says that whether I say mod f is measurable or I say f is measurable, that is the same thing,
Yes, sir.
right? And I have
And
just proved that mod f is measurable.
yes, sir.
So it means f is measurable.
Yes, sir.
Okay. Now once f is measurable, can we write this given set capital A as the pre-image of some Borel set under f?
This fx.
Yeah. So okay, let me write the question for you. Let us forget this. So the question is, can we write A as the pre-image of a Borel set? So E comes from the Borel sigma algebra of R. Can we do that? Then look at the definition of F and tell me, can you do that?
Yes, sir. Thinking, sir.
See, what do you understand by this symbol, F inverse E?
So the pre-image of E.
But how do you define it? This is a set, right? So you have to
Yes,
collect points. So
x
collect all
belongs
those.
to such that
Hmm,
x is fx belongs to E.
correct. So that fx belongs to E, right?
Yes,
Now, this fx can take only two values, either 1 or minus 1,
yes, sir.
right? Now, if I want this to be A, if I want this to be A, then what does it mean? It means that this 1 must belong to E, correct?
Yes, sir.
So this F inverse E is equal to A if and only if 1 is inside E. Now, what are all the sets that contain 1? Right, that should be Borel sets also. And yeah, in fact, and minus 1 does not belong to E, right? Because if minus 1 also belongs to E, then it would be A union E complement, the whole X would come out.
Yes, sir.
So now tell me, what should it be? What should your choice of E be? There are many choices, right?
Yes, sir.
Any one. Tell me any one that works.
The choice of
Choice of capital E. You tell me. You tell me one set of R, which is a Borel set, and it contains one, but it does not contain minus one.
can be any open set which belongs in which one belongs, and obviously minus one we have to exclude the minus one.
Okay, but you give me one example of that.
I think the open interval 0 comma 2.
Okay, open interval 0 comma 2. Let us do this. E open interval 0 comma 2. This is inside the Borel sigma algebra, right? Why?
Yes,
Because
sir.
it is an open set and Borel sigma algebra is generated by all the open sets. So this
Yes,
must
sir.
be inside BR. Okay. And then F inverse E is A, correct?
Yes, sir.
Now F is measurable. So the pre-image of a Borel set is measurable. So this is inside S.
Yes, sir.
Have we proved that the power set of X is equal to S? So does this imply that S is equal to power set of X?
The pre-image of any open set, yes, belong to the sigma algebra.
Yes. Are you saying something, Prasandeep?
So we have proved that any open set, the pre-image of any open set belongs to the sigma algebra.
No, no, that is not what we have proved. See, what is the definition of measurable functions for us? Can you tell me what is the definition of measurable functions?
Yes, sir. The pre-image of in the Borel sigma algebra, we or any general.
No, this for a function from a measured space to R. What is the definition of measurable functions?
The pre-image of the intervals must be measurable.
Pre-image of intervals will be measurable, or pre-image of every Borel set must be measurable, right?
Yes, sir. In this Borel sigma algebra.
So f from xs to r br, this is measurable if for you take any Borel set of R, the pre-image of that Borel set is inside of S. This is the definition, right?
Yes,
Or
sir.
one of the equivalent statements for measurable functions. So once we have this, and we have proved that f is measurable, so this f inverse E must be inside the sigma algebra S, right?
Yes, sir.
So we have not proved that every pre-image of every Borel set is in sigma algebra. We have proved that you start with any subset of X, that subset is inside the sigma algebra. You have still not
Okay.
understood it.
Yeah, yeah. Okay.
Okay. So now does this imply that S is equal to power set of X?
Yes, sir.
Does that clear your doubt?
Yes, sir. We have taken any subset of X and prove that obviously any subset of X, arbitrary subset of X, prove it that it is belongs to S. Yes, sir. Now get it.
Yeah, but do you understand the technique? How did this come inside us? That is more important.
Yes, sir. We have taken that we have defined a function. We have used a
Mm-hmm.
which is both wise measurable. Both f is measurable implies mod f is measurable, and we have used that function to show that obviously the sigma algebra is equal to power set of x.
Correct. So, you have to construct this function, right? This f is our construction. Now one
Yes,
can define, some different way, but this is the simplest way because we know that constant functions are measurable. So mod f becomes constant function, and therefore we can proceed very easily.
sir.
Okay. So, any other questions from week 6 or anything else? Any questions from the YouTube audience? No. Okay. Yeah. Do you have any other questions for Sandeep?
Yes, sir. I have sent you a email regarding the assignment in
Yeah,
which
but
the I think the
already posted it, right? I already posted it there.
okay, okay. So am I right? Was I right that
Yes, yes.
problem?
Yeah, yeah, you were correct.
Yes, sir. Please inform the NFTL team so that obviously our score will be affected in the
Yeah, actually,
certification.
what you can do is if such a thing happens, you can post it in the discussion forum.
Yes,
Then, because discussion forum is open to everyone, then people can see that.
sir, I have the issues.
Uh-huh.
Yes, sir. But I have I have to talk to somebody like you to obviously that our that
Yeah, yeah, yeah. That
it,
is
it
that
it
is fine.
will be rectifying on.
That
Yes,
is
sir.
fine. But yeah,
Okay.
if you are,
Yes.
very sure that, there is some issue with the questions, because I have observed that there are some typing errors as well in one of the assignments. So if you are very sure that
Okay.
there is a problem with the questions, you can also post it in the discussion forum. That will not be a problem. Okay.
Okay. Okay. Okay, sir. I will do it in
Okay.
future.
Yeah. Any other thing? Any other questions?
No, sir.
Okay. So let us, I wanted to discuss something today. Let us do that.
Okay.
Uh, Let me start with an example. I have sort of constructed it, but it is not very difficult. I am going to give you a simple function, and I want you to tell me what are all the values that it takes. So,
Okay.
or perhaps Let us not call it simple function. I'm going to give you a function. We'll see whether it is a simple function or not.
Okay.
So let us define S from R to R as follows, or R to R star, doesn't matter. Mm, S of x is equal to sum from I 1 to 5 I times chi ai, where ai's are as follows. So a1 is minus 1 to 3 by 2, a2 is 0 to 1, a3 is half to 2, a4 is 3 to 5, and a5 is 4 to infinity. Okay, so these are five sets, and this is a
Okay.
linear combination of these characteristic functions. I am not calling
Okay.
it a simple function for the time being.
Okay.
So you tell me what are all the values that this S takes?
What are the values that?
S takes. So what is the range of S? I want to know that. Or perhaps what we'll do,
Yes,
let
I
us,
think the finite values 1 to
uh,
5.
is it only 1 to 5? Do you mean to say that the range of S is equal to 1, 2, 3, 4, 5?
I think the sets you are defined are not mutually disjoint in.
Right, right. That is why I'm not calling this as a simple function. If they
Yes,
were
sir.
mutually disjoint and the union would be R, then I would have
Yes,
called
sir.
it a simple function. But this is not a simple function. This is just a linear combination of some characteristic functions.
Yes, sir.
Okay.
So
So
it
this is
will
not
take
true, right?
bigger values then.
Yeah. So this range is not 1, 2, 3, 4, 5. Let us see what
Yes,
this
sir.
range is. Where should I draw? At the center is better. So let us try to draw. A1 is minus 1 to 3 by 2. So this is minus 1 and perhaps this is 3 by 2. A2 is 0 to 1. 0 to 1. A3 is half to 2. So half to 2. So I should really use some colors. So from here to here we have A1.
Okay.
This one is, so from here to here we have A2. From this to this is A3. And then what is next? 3 to 5 and 4 to infinity. So this is 3 to 5, 4 to infinity. So this one is A4. And from this onwards we have A5. This is an infinite interval. Okay. Now let us look at, if we have a point between, I mean, we have a point less than minus 1 somewhere here. What is the value of S here before minus 1?
If point less than minus 1,
Yeah. If X is less than minus 1, then what is the value of S?
obviously it will be 0.
0, right? So everywhere here, the value is 0.
Oh,
Okay. What about when X is between minus 1 and 0? So maybe I'll start writing. Sx is 0 when X is less than minus 1. What is the value when X is between minus 1 and 0?
so it will be, I think, 1.
It is 1, right? Because it is inside A1, but it is not inside any other set.
Yes, sir. It is not inside any other cell.
So from here to here, it is 1. Okay. What happens between 0 to half?
Between 0 and
Half. Because see, I have like sort of partitioned this. So let us look at these smaller intervals. Let us see what happens there. What happens between 0 to half?
0 to 1, can be 3.
It is 3, right? Because it is
Yes.
inside A1 and A2 and no other sets. So it is 3. What about half to 1? Now it is inside A1, A2 and A3. So it is 1
Yes.
plus 2 plus 3. It is 6. Correct?
Yes, sir.
And then from 1 to 3 by 2, what all sets are contained here? In 1 to 3 by 2, A1 is there,
Yes, sir.
A3 is there, right? Only A1 and A3 are there. So it is 4.
Okay.
Yeah, but not really drawn. So let me draw 0 to half 3, half to 1 6, and then 4. 1 to 3 by 2 4. What happens after 3 by 2? So 3 by 2 to 2. It is only in A3, right? It is only the part of A3, not any other set. So it is just 3.
Oh,
So this is only 3. Yeah. Now you tell me the remaining ones. What about 2 to 3? What happens here?
it is
The
obvious.
point is here. Yeah. It
2
is
to
what?
3.
Ah,
2 to 3.
yeah. 2 to 3.
It is obviously 0.
0, right? So it is 0 when it is 2 less than x less than 3. Okay. What about 3 to 4?
It is 4.
It is 4. Why? Because it is only in A4 and no other set. Okay. And what about the last one? 4, I mean, okay, not the last one as such. 4 to 5?
It, what is the interval A5?
A5 is 4 to infinity.
4 to?
4 to plus infinity. It is unbounded on the right.
It will be 9. The value is
It
9.
is 9, right? It is 9. Okay. And then the last one after 5?
It,
What
it
will
will
that
be
be? Yeah, tell me, what is it?
after 5, then it will
Yeah,
be 5 value.
it is 5, right?
Yes.
It is 5. Okay. So after 5 is 5, so we're here. Okay. The graph really doesn't matter. Okay, so first you observe that here in all these values, 2 is not there, right? So
Yes.
initial guess that the range should be 1, 2, 3, 4, 5. That is not correct. In fact,
Yes,
it
sir.
is, there are 6, 4, 6 and 9 also, and 2 is
Yes,
not
sir.
here. Okay. But now, just by looking at this, can you tell me whether S is a simple function?
So in a simple function, in the definition, the mutually disjoint is
Yeah, it is required. In the definition, it is required.
so we can construct it. It is a simple function. Then
This one, right? This S.
we can construct it as a simple function
How?
if it is not given that it is mutually disjoint intervals. We
Uh-huh.
by the
Yeah,
range.
how do we do that?
So we define the intervals according to the values of the function, that is the range, the values in the range.
Exactly.
And
So that is
yes,
what that is what we have been doing here, right? We are
yes,
splitting this bigger intervals into smaller parts where I
yes,
can
sir.
get a single value. Okay. So this S basically, this can be written as summation AI chi AI, where these AIs are mutually disjoint and their union is all of us. Now notice that initially I had only 5 intervals, but now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total
Yes,
intervals, right?
yes, sir.
So it doesn't really, it is not necessary. that if I start with n number of intervals and then I break it, I will still remain with n number of intervals. Sometimes intervals can change.
Yes, sir.
So, okay. So this was for, just giving a intuition that a linear combination of characteristic functions, it can be broken down as a simple function. But how to prove it? That any linear combination can be done so. So let us try to do that now. Result which we want to prove is that any linear combination of characteristic functions is a simple function.
Yes.
So how do we prove it? Suppose I write it like this: S is summation ai pi ai. Okay? And this, of course, ai's are not necessarily mutually disjoint. Not necessarily mutually disjoint, and union ai is may not be equal to x. In this case, how do we split it? What should we do?
Mm, its union is not equals to the set X. Then we have to obviously consider it in a way that the union of this the news AIs will be equals to X.
Correct. So how to do that? So let us first attack this one, that if this is not equal to x, how to make this equal to x.
Yes, sir.
Okay. So any ideas how to do it? Yeah,
We
certainly.
have to define a new set. We have to introduce a new set,
Yeah, yeah,
maybe
yeah. Which set we will introduce? That's what I'm asking.
complement of union of AIs.
Exactly. So even though this is not equal to x, we know that this union with this complement, this must be equal to x, right?
Yes, sir.
Okay. So all right. Now this is fine. Also, if I call this as, say, maybe let us call this set B. Okay. Then B is disjoint with every AI.
Yes, sir.
Do you agree with that?
Yes, sir.
Okay. Now somehow I want to make this mutually disjoint.
Yes, sir.
So how to do that? I also noticed that we have to add these things. Huh? This
Yes, sir.
to be taken into consideration. So what will we do? Any ideas behind it? See, let us look at this example. What we did was we first saw all those points which are in exclusively in only one interval. For example, these points between -1 and 0, they are only in A1 and not in any other AI, right? The
Yes, sir.
points in 3 by 2 to 2, they are only in A3 and not any other AI. Similarly, points after 5, they are only in A5 and not any other AI, right?
Yes, sir.
So let us do that. So we will write this. So whenever such a thing happens, that only AI comes outside. There is no other addition to it. So let us
Yes,
write
sir.
this S as summation I from 1 to n AI pi AI difference union j from 1 to n j not equal to I AI. Okay. So what does this mean? We are collecting those elements of AI which are not in any other AI.
Yes.
Maybe I will write AG. Collect those elements in AI that are not in any other agent. Okay. But this does not help us, right? Because now we have excluded a lot of parts. For example,
Yes.
we may have a situation like this. Uh, Maybe something like this. So this is our A1, this is A2, this is A3, and this is A4. We have only included this part, this, and then this, and this part, right? There is still
Yes.
a lot of points which are not we have included. So to include those, what will we do? Let us now look at the intersection of two sets, right? Those points which are in A1, A2, but not in A3, A4. Those points which are in A1, A3, not in A2, A4, and so on. So I1 from 1 to n, I2 from 1 to n, and let us look at I1 less than I2 because I do not want any repetitions.
Yes.
And then in this case, it would be AI1 plus AI2, pi of AI1 intersection AI2, difference with union j from 1 to n, j not equal to I1, j not equal to I2, AJ, right?
Yes.
So basically, what now we are doing is let us look at say only this. Maybe I'll use some different color. This part, and then A1, A3, which are not in any other. So this part, A1, A4, which is not in any other. So this part. Okay. So we have seen this, but still there are some points remaining, right? So we have to collect them. So to collect them, what I will do, I will take three intersections, and then I will keep on doing this until I reach the last one. The last one is intersection of all those things, which is this part, right?
Yes.
So the final one would be A1 plus A2 and so on. An chi A1 intersection A2 intersection A3 and so on. So now this is fine. Plus we have to add this B plus
Complement.
0 times pi B.
Yes.
Now is this a simple function? So see, it looks very tedious to actually compute. But yeah, is this a simple function?
Yes, sir. We have construct in a way
Right.
that
So we have sort of split this whole union into smaller mutually disjoint subsets. And on those mutually disjoint subsets, we have actually found out what is the value of this function, right?
yes, sir.
So this is in fact a simple function. So what we have proved? We have proved that any linear combination of characteristic functions, it can be written as a simple function, whether or not those characteristic functions are mutually disjoint.
Yes, sir.
Now, another observation that we can make is if we have a simple function, then its range is always finite because it is a linear combination of characteristic functions, right?
Yes. And sir, the coefficient would be the would have to be the real numbers. Actually.
Right, right. Yes, yes. So observation is range of a simple function is finite. So the question is what about the converse? If s from x2r or x2r star is a function such that range of s is finite, is s a simple function? Yeah, this is the question. What do you think? Is s going to be a simple function?
So it may not be a simple function because obviously we have done it earlier that if the set are not mutually disjoint, then actually it will not be a simple function.
No, no. But we can write that thing also as a simple function, right? That is what this result says. Any linear combination of characteristic functions is a simple function.
Yes, sir. Then I think it would be a simple function
Right. So
because we can.
it should be a simple function, right?
Yes,
So
sir.
let us write it. So range of S, let us write A1, A2 up to AN. Okay? And let us define sets, define AI, yeah, where AI is not equal to AJ or I not equal to J. Okay, because writing a set means we are not allowing any repetitions while writing.
Yes,
Define
sir.
AI as S inverse small ai. So this is a subset of X. And is this AI intersection AJ empty for I not equal to J?
Yes, sir.
No, it is empty, right? Because
Yes.
this AI and AJ are different, so no point can have like two distinct images under S. So AI
Yes.
intersection AJ is empty whenever I not equal to J, and union of AIs is all of X, right?
Yes, sir.
So we can just write this S now as AI by AI. Do you agree with this?
Yes, sir.
So any question in whatever we have done till now?
No, sir. Yes.
So we have rather proved this result that a function S from X to R star. This is
About
simple.
taken AI such that their union should be equal to X. And we have construct in a way. Am I right?
I couldn't understand the question.
In the proof above, you have written the union of AI should be equals to X. So we have taken the AI should then their union must be equals to X. We have taken
Actually,
the actually
yes,
that.
yes. Why
है
is
ना?
this true? Yes, yes. Why is this true? Let us write it. 1 to n AI. This is union I from 1 to n. S inverse small ai, right? Which
Yes,
is
sir.
union I from, I mean, oh, sorry. It is basically S inverse of this range A1 to AN. But S inverse of the range must be all of X.
Yes, sir.
So does this answer your question?
Yes, sir. If range is finite, then the function that function would be a simple function.
Right. So we have proved it. In fact, we have proved that if like a function is simple, if and only if the range is finite.
Yes, sir.
Okay. Now, uh, let us discuss one more thing. Do you recall how we defined Riemann integration? Have you studied Riemann integration?
Yes, sir.
How did we define it?
So we take a partition of the interval in which the we have to define the integral, and obviously we take the part obviously
Yeah.
upper sum.
So yeah, first what we require is we require a closed and bounded interval, right?
Yes, sir.
So let us start with a closed and bounded interval. Let us take only non-negative function for the time being, because negative functions actually that requires uh, taking the non-negative part and the negative part and all those things. So let us take a non-negative function. Suppose the function is like this from A to B. What do we used to do there in Riemann integration?
So we take the upper sum and then the lower sum of the partition, and then
Yeah.
we define the.
So first we take a partition, right?
Yes, sir.
So A1, A2, A3, A4, A5. So perhaps this is A6, and this A we call it A0, right?
Okay.
This is what we used to do, right? Or you used to
Yes.
do something different?
Yes, sir.
Now what do you do? What do you mean by upper sum and lower sum?
So the value of the function, the supremum value of the function in that subinterval, and then we take the linear combination and add that in the
Right. So
whole interval.
basically, what we want to do is we want to find out the area under this curve, right?
Yes, sir.
And we don't have any direct method of calculating the area. But what do we know? By geometry, we can find out the area under rectangles. Because area of a rectangle is length into breadth. So let us
Yes, sir.
divide this whole area into some rectangles. Perhaps we'll leave some area out, or we will include some extra area that we'll see later how to get rid of that. So first, let
Yes, sir.
us just partition this whole thing. Okay. Now, inside this A to A1, let us look at the infimum of this F. So it is this, right? Let us look at this rectangle. Inside A1 to A2, let us look at this rectangle.
Yes, sir.
Then A1 to A3, the infimum is where? This one is the infimum. Let us look at this rectangle. A3 to A4, let us look at this rectangle. And then A3, A4 to A5, this one, and then again this one, right?
Yes, sir.
And then add them up. We say that the total area, mm, total area should be bigger than or equal to the green area, correct?
Yes, sir.
Because in fact, what we have done, we have left these parts, right? These brown parts we have left. Okay. The other thing which we can do is let us look at the supremum. So let us look at these bigger rectangles. So this one, and then A1 to A2, we have this big rectangle. A2 to A3, again, this rectangle. A3 to A4, this another big rectangle. A4 to A5, this rectangle. And A5 to A6, it is the same as the green one. And then let us calculate it. So this thing, total area, is less than or equal to the red area.
Yes, sir.
And why is that so? Because we have included all these extra portions, which we don't want. So how to get rid of these extra portions? Let us shorten the partition. Let us make this partition even finer. Then
Yes,
we can reduce that extra area, and we can include the more area from below, right?
yes, sir.
That is the idea. So the idea is to approximate the area under a curve by using rectangles from below and from above. Now, this is all in Riemann integration and all this is fine. What we now want to do is we want to do this for measurable functions. So that measurable functions may not be continuous, right? I cannot really draw the graph of it, but I want to do a similar thing for measurable functions. So for that, let me define a few things. So let x
In
be,
it, it is also true that the function is not continuous.
what is true if the function is not continuous?
In Riemann integral,
Mm-hmm.
you
Yeah,
have defined a but
because
Riemann integral.
right. But the motivation of defining Riemann integral was to calculate area under continuous curves,
Okay.
right? That is the initial motivation. Then we extend it to discontinuous functions. But even then, we have this problem that the discontinuities, they cannot be, I guess, what do we say? Either there are finitely many discontinuities, or if there are infinitely many, then they must have a limit point, right? That is some
Yes, sir.
result.
Yes,
So
sir.
uh, that is required. Now let us take a measure space. Okay, and let us collect some subsets. Let me call it P, even to En. This is a collection inside S. So these are all measurable subsets. This is a measurable partition. If Ei intersection Ej, this is empty for I not equal to J, and union of Ei's is all of.
Okay.
Okay. So we are trying to mimic this idea exactly as it is. So here we partitioned the interval into smaller subintervals. Now we want to partition all of the measure space into smaller measurable sets. Okay.
Yes, sir.
Now, given a non-negative function, okay, so I am going to assume a few things that will be clear later why I am assuming that. So assumption is that the measure of the whole space is finite and f is a non-negative measurable function with f bounded. So bounded means there is some capital M such that okay, I don't need to write mod fx. Take any x, fx is less than or equal to M. So it will be clear why we require it. But yeah, for the time being, let us just assume that the measure is finite and f is a bounded measurable function.
Okay.
Okay. What I'm going to do is let us define capital Mi as the supremum of f of x, where x varies in ei, and small mi as the infimum of f of x as x varies in ei. So notice that here also we did the exact same thing. In each of the smaller subintervals, we looked at the supremum of function, looked at the infimum of function, and made the rectangles, right?
Yes.
So here also, inside this smaller measurable set, I am looking at the supremum of f and the infimum of f. And then let us define uh, two more functions Pp as summation small mi chi ei and Cp as summation capital Mi chi ei. So are these simple functions Pp and Cp?
Yeah, because sir, the EIs are disjoint.
The EIs are disjoint, so and the union is whole of x with their simple functions. In fact, they are
Yes.
measurable simple functions because EIs are measurable and they are non-negative because f is non-negative. So this is inside L0 plus. Now there are two things. To get this mi finite, this is finite because f is bounded. Right? If f was not bounded, this could be plus infinity, and I
Yes.
don't want it to be plus infinity. So let us take a bounded function. So this capital Mi is finite, this small mi is also finite. Yeah, do you agree?
Yes, sir.
Okay. Now let us do one thing. Uh, let us collect. So these are simple measurable functions. So I can define this integral phi p, right? This is well defined. Similarly, this integral of Cp is also well defined. Do you agree?
Yes, sir.
Let us collect them. Let us look at a set. Maybe what should I call it? Let us call it S1. S1 is a set of all these integrals of phi p, where P varies as a measurable partition. Let us look at S2 as the integrals of Cp, where P is a measurable partition. Okay. Now, can we say that integral of Pp is less than or equal to integral of f, and this is less than or equal to integral of Cp? Can I say this? Are you there?
Yes, sir.
So can I say this, that this integral Pp is less than integral f and it is less than integral Cp?
Because that of infimum and supremum.
No, no, not because of infimum and supremum. See, Pp is always less than or equal to f, right? And f is less than or equal to Cp. Isn't that the case?
Yes, sir.
Yeah. So their integrals must satisfy this inequality because integral is a monotone operation.
Yes, sir.
Yeah. Okay. So, all right. Now we have this. So therefore, this supremum of S1, this is less than or equal to integral f d mu, and this is less than or equal to the infimum of S2. Do you agree with this?
So in S1, the P is a measurable function of S. Then the supremum of that.
P is a measurable partition of X.
Okay.
Yeah. So P is varying. So I can take the supremum over all those P's, right?
Yes, sir. Supremum.
So the supremum of S1 is, it cannot exceed integral of F because for
Yes.
every P, we have this inequality with us.
Yes, sir. Supremum can't exceed it.
Similarly, the infimum cannot be less than integral of
Yes.
F, right? Okay. So now the question is whether we have an inequality. The natural question to ask is whether they are equal, right? So let us see. Let us start with say, oh yeah, you just tell me, has this been proved in the class? Integral of f d mu. This is equal to supremum of integral s d mu, where s is a non-negative simple measurable function which is less than or equal to f. Is this done in the class?
I have not seen that lecture of week 7.
Oh, we have
I
not.
have seen the first lecture, which
Okay,
is
so I think that this may be done. If it is not done right now, it will be done at some point. So you just
okay.
assume that this is true, this green result. So integral of f d mu is supremum of the integral of the simple functions s, which are less than or equal to f. So, what does this mean? It means that for every epsilon positive, there is a simple non-negative measurable function which is less than or equal to f, and integral of s d mu, this is strictly greater than integral of f d mu minus epsilon, because this is the
Yes,
supremum and this is minus something will no longer be an upper bound. Yeah.
yes, sir.
Okay. Okay. So we have this. Now I can write S as summation ai pi ai, I running from 1 to n, where if I write this p as a1 to am, this is a measurable partition of it. Yeah. Do you agree with this?
Yes. Yes, sir.
Okay. So since this is a measurable partition, I can talk about phi p. Phi p at x is summation I from 1 to m mi chi ai. Can I say that this is bigger than or equal to s of x?
In left hand side, the MIs are the infimums.
Yes.
Yes.
So can I say this? See, because Sx is a lower bound of fx, right? And mi is the infimum of
Yes.
fx. So mi must be at least Sx.
Yes, sir.
Yeah. So we can see this. Now, once this happens, integral of phi p is greater than or equal to integral of s, which is further bigger than integral of f d mu minus epsilon. Correct?
Yes, sir.
So from here, can we say that supremum of S1 is exactly equal to integral of f d mu?
Yes, sir. Because epsilon is arbitrary.
Correct. Because we have already
Yes.
seen that integral f d mu is the upper bound, and we have proved that integral f d mu minus epsilon is no longer an upper bound, right? So it must be the least upper bound
Yes.
or the
Yes,
supremum.
sir.
So therefore, this supremum, or rather, I have characterized the integral of f in this manner. Integral of f d mu is equal to supremum of integral of phi p d mu, where p is a measurable partition. And how is this phi p defined? Phi of the partition p at x is summation mi chi ei, I from 1 to n, where mi is the infimum of fx as x varies in ei. Okay. So now can you see this that the measure, the definition of this integral through this measure space is just the extension of the definition of the Riemann integration. Yeah. Hello.
Yes, sir.
So
The
do you understand
extension
what
of this,
what point I want to make?
thus the definition of measurable, the Riemann integral is the we have defined some extension.
Correct, correct. So the way we have defined the integration of a measurable function, it is just the extension of the Riemann integration, right? So it is a
Yes, sir.
natural way to define it. That is what I want to say. Okay. Now the next question, whether the infimum of S2 is equal to integral f d mu. And here is the point where this measure of x is finite will come into picture. So for that, let us look at this function. Let us define g as m minus f. So is this a non-negative measurable function?
Yes, sir. Because we have defined G is equals to M capital M minus M, that is the supremum.
Yeah, m is, yeah, it is supremum. It is actually an upper bound of f. So this is a
Yes, sir.
non-negative function. And why is it measurable?
So because F is measurable and M we can take it as the constant function. We
Exactly,
can
because m is a constant function m, and f is
yes,
measurable. So linear combination of two measurable functions is measurable. So this g is measurable, right? Now, if this g is measurable, we can correspondingly define this PPG as summation MIG chi EI, where MI of G is this infimum of GX, where X belongs to EI, right?
Yes.
But this I can write infimum of M minus Fx as X belongs to EI. And yeah, you tell me whether we can write it like this. This is equal to, I don't know, M minus supremum of Fx as X belongs to EI. Can I write this? Yeah.
So infimum of m minus fx, that is a non-negative set, and then it is equals to m minus supremum of fx.
Yeah, but is it true? That I have written already, but is it true? Can you prove it?
So I'm not right now. I'm not getting
Okay.
it. It is true or not?
So what I will suggest is I'll give you one exercise. You try it, and if you're not able to do it, you can discuss later.
Okay.
So maybe exercise is this: let A be a subset of R, and let X be in R. Then supremum of X plus A is X plus supremum A. Infimum of X plus A is X plus infimum A. Supremum of minus A is minus of infimum A, and infimum of minus A is minus of supremum A. Okay?
Yes, sir.
So you prove these four things, and we have used
We
this
have
four here.
used the fourth one actually. We have.
So no, we have used the second and fourth because I have to
Yes,
take
sir.
this M outside, and then
Second,
I have
fourth.
used the fourth. Yeah.
Yes, sir.
So you prove this exercise, then it is clear. Okay. So this small mig is capital M minus capital MIF. Therefore, this PPG is actually I from 1 to n m into chi ei minus sum I from 1 to n capital MIF into chi ei, which I can write m minus CPF, right?
Yes, sir.
Okay. Now, again, for any epsilon positive, there is a partition P such that integral of CPG d mu, this is bigger than integral of G d mu minus epsilon, right? Because of whatever we proved above, that, integral f d
Yes,
mu
sir.
can be written as this supremum, correct?
Yes, sir.
Okay. Now let us expand this. So this is integral over x, m minus CPF d mu. This is bigger than integral over m minus f minus epsilon. Yeah, I have
Yes.
just written the definitions of everything. Now, see, this m minus f, integral of x, m minus CPF, this is finite because the measure of x is finite. Otherwise, this integral of m will cause a problem.
Okay.
right? So therefore, we require this another assumption that measure of x is finite, and that is why I
Yes.
wrote it in the very beginning. Okay. Now what I will do, I will take this on the left hand side. I will do some manipulation. So integral of m minus CPF d mu minus integral of m minus f d mu. This is bigger than minus epsilon, right?
Yes, sir.
But then due to linearity, integral of f minus CPF, this is bigger than minus epsilon. Yeah?
Yes, sir.
Or what is the same? Integral
It
of
is.
CPF d mu. This is less than integral of f d mu plus epsilon.
Yes, sir.
So this was a lower bound for S2, but this whole thing together with this plus epsilon, this is not a lower bound for S2. What does this mean? Can I say that infimum of S2 is equal to integral f d mu?
Yes, sir. Because of that,
That is the definition of infimum, right?
not
So
a
what
lower.
we have essentially proved this result. If the measure of the whole space is finite and f is a bounded measurable non-negative function, then integral of f d mu, this is equal to supremum of integral pp, where p is a measurable partition. It is also equal to the infimum of cp, where p is a measurable partition. And what are these pp and cp? Cp is the simple function small mi chi ei. Cp is the simple function capital Mi chi ei, where small mi is the infimum of fx as x varies in ei, and capital Mi is the supremum of fx as x varies in ei.
Yes, sir.
So is this clear?
Yes, sir.
So actually we have exceeded a lot of time. Let's not discuss what I want to discuss next thing. But I'll give you a thinking exercise. You
Yes.
can think about it, and in the next discussion we will discuss this. If f from x to r or r star is any function or any measurable function for that matter, does there exist a sequence of simple functions Sn from x to r star such that Sn is bigger than or equal to s and Sn converges to s pointwise, or rather, decreasing sequence I want. So we have seen that, measurable functions can be approximated from below using an increasing sequence of simple measurable functions. Now I am asking the other way around question. Given a measurable function, can we approximate it from above using simple measurable functions?
Okay.
Okay. So you think about it
Okay.
and we'll
Okay.
discuss it in the next time. So
Okay,
any
sir.
other
Thank you.
questions you
No,
have?
sir.
Okay. So let
Thank you,
us
sir.
stop. Thank you.